Lecture slides for lecture 28. This would normally have been held on the 24th of March this year and would have been the last lecture of this semester. This lecture is concerned with modelling strategy. Basically, we're interested in how do we choose what we would consider to be a good model. And we start off by contrasting two different types of approach to this. One is what we call the specific to general approach. The other is the general to specific approach. Basically, the difference here is between starting with a model which is very restricted and then relaxing the restrictions, or starting with a model that's very unrestricted and testing restrictions as we approach a more parsimonious specification. That requires us to talk about the issue of specification searches, and then finally we'll talk about the idea of error correction representations of the model, which are basically the sort of model we end up with after we've conducted a specification search. Let's start off with a basic caricature of how statistical modelling takes place in textbooks. The textbook approach assumes that we conduct experiments in order to generate our data. So we start off by choosing values of the x variable and then conducting an experiment which generates a set of values for another variable y. And we repeat this however many times we choose to. Every time we repeat it, the result of the experiment is affected by random errors or unforeseeable events. By doing this sequence of experiments, we generate a data set, and the data set allows us to investigate the relationship between the input variable x and the output variable y, using a relationship of the form y equals beta x plus a random error term u. We then use that data set to estimate the unknown parameters of the relationship between y and x, i.e. the beta parameter, and we use a method like least squares. And basically, using this approach, we can be as precise as we want, because we can continue to repeat the experiment any number of times. Fortunately, as we know, that's not the way in which things work in economics. A more realistic way of thinking about econometric modelling is that y and x are generated by some unknown data generation process. So we observe values of y and x, but we have no control over them. So what we're interested in doing is investigating that data generation process using the data. So we start off by making a set of assumptions about the data generation process. In other words, we set out a model. And then based on that model, we estimate the parameters. We then go back and we test the assumptions of the data generation process. We say, is the model that we've estimated a good model? If necessary, we revise the assumptions about the data generation process and we go back and re-estimate our parameters until what we get is what we consider to be an acceptable model, an acceptable representation of the data. Now, there are different ways in which we can approach this process. For many years, the standard approach in econometrics was what we call a specific to general approach. And basically, it works like this. We start off with an equation that's based on economic theory. Okay, for example, the demand and supply model. We then estimate the equations that characterize that theory using an appropriate technique, ordinary least squares, instrumental variables, or whatever. We then check for statistical problems associated with our estimates. In other words, we do diagnostic tests. We test for serial correlation, heteroscedasticity, and so on. And if the equation fails that test, then we re-specify it. We look for an alternative specification. And we continue doing this until the equation performs satisfactorily. Now, it's quite likely that you've done something like this in your assignment. The problem is this is not necessarily the best way of approaching econometric modelling. There are basically problems with this approach. First of all, the basic problem is that if the equation we estimate is misspecified, then statistical inference based on it will be unreliable. If we've got, for example, serial correlation in our equation, we know that t-tests and f-tests based on that equation are going to be unreliable. They're not going to have the correct distribution. Usually it's a matter of we've not estimated the standard errors of our parameters correctly. Another problem, problem 2 here, is that if we've got a misspecified equation, for example we've got serial correlation, it can show up in failure of multiple diagnostic tests. So we don't just get a failure of the serial correlation test, we may get a failure of the heteroscedasticity test, of the functional form test, or whatever. Okay, so we're not always sure just why an equation is failing a test, because it tends to fail across the board when we have misspecified equations. The third problem is it's not always clear how you respecify the equation in order to make it perform better. You'll have seen in your projects, for example, if you've got serial correlation, you can include an AR1 term, you can difference the data, you could try other strategies such as including other variables like a time trend and so on. So it's not always obvious how you go about getting a better equation, and depending on the choices you may end up with radically different models based on the same initial data, the same initial estimates. Okay, let's start being a bit more specific about this. Suppose the true model that we should be estimating is one that includes both x1 and x2 as explanatory variables. So it takes this form here, y equals beta 1 x1 plus beta 2 x2 plus an error term. But we estimate y equals beta 1 x1 plus v. The problem we've got with that straight away is that OLS estimates of the parameters will be biased unless it just happens to be the case that x1 and x2 are uncorrelated. Moreover, since the composite error term in our estimated equation v is a combination of the original error term u and the effect of the emitted variables beta 2 x2, the errors in the estimated model won't have the Gauss Markov properties. We cannot rely on inference based on OLS estimation. So, what do? Well, an alternative is to adopt the strategy of general to specific modelling. And this became fashionable in the 1970s and has dominated British econometrics, at least since then, through the work of what was known as the LSE school at the time, particularly the work of David Hendry and associated co-workers. And general to specific modelling argued for a different approach. Basically, for general to specific modelling, we should begin with a very general model, including usually as many lags as possible. Has to be said, the general to specific approach focused very much on time series data modelling, though in particular it could be applied to cross-section modelling as well. Anyway, we begin with this very general model in order to try and encompass as many possible models or specific models as we can. We saw in the previous lecture that if we start with a model with lots of lags, a general ARDL model, then lots of the special models that would be considered as special cases of that. When we've estimated a very general model, we then simplify it by eliminating insignificant variables to obtain what we call a parsimonious specification. We try and get rid of the insignificant variables by testing for the significance of the variables included and eliminating the insignificant variables. And then finally, if we're dealing with time series data, then a useful way to finish our model is to rewrite the final specification in what we call error correction form in order to make it easier to interpret. Okay, what are the advantages of this approach? Well, the basic advantage is because the initial model is very general, it's less likely to be misspecified than the sort of very tightly restricted model we would start off with in the specific to general methodology. The second advantage is that instead of imposing a particular dynamic structure on the model, the specification search procedure allows the data to determine the shape of any distributed lag relationship between the y and the x variables. Okay, so we're not sort of making any assumptions about the relationship, we're allowing the data to determine that dynamic relationship. And then finally, because in the general to specific approach, we hopefully start off with a well-specified equation where the errors have got standard Gauss-Markov properties, then we test for misspecification at every stage, so all our tests will be valid, and the final model will provide a balance between obtaining a well-specified model and a restricted or parsimonious specification. Why do we concentrate on this idea of the parsimonious specification? Well, the answer is we don't want to include too many variables in our regression equation because there are problems associated with including irrelevant variables. In particular, if we include irrelevant variables, we tend to get inefficient estimates. Okay, the standard errors of our coefficient estimates will tend to be too high. And that is a particular problem with time series data because of the problem of collinearity. Suppose, for example, the true model was y equals beta 1 x1 plus u1, but we'd included an irrelevant x2 variable in our regression equation. Now, using standard formulas that we've developed in previous lectures, if we include x2 in the regression equation, the variance of our estimate of the beta 1 parameter would be sigma squared, which is the variance of the error term, divided by the sum of x1 squared multiplied by 1 minus r12 squared, where r12 is the sample correlation coefficient for x1 and x2. Okay, that's a standard result, we derived it in previous lectures. And if x1 and x2 happen to be correlated with each other, and in general with time series data there will be some correlation between the variables, then this variance is higher than the variance you would obtain if you were to exclude the x2 variable from the regression equation. Basically, the variance, if we exclude the x2 variable, would just be sigma squared over the sum of x1 squared, and we're multiplying that by 1 minus r12 squared when we include the x2 variable, and since we're multiplying by a number that's less than 1, that's reducing the value of the denominator and it's increasing the value of the variance overall. So that's why it's important to get the parsimonious specification. The inclusion of irrelevant variables like x2 in the regression equation increase the variance of the parameter estimates of the coefficients that we're interested in. Okay, well, let's start to look at an example here. This is the sort of way in which we would apply this methodology. Suppose we're estimating a model for stock building. So we're looking at the relationship between stock building and changes in GDP. So SB here is stock building, DY is changes in GDP, and we start off with a general autoregressive distributed lag model. This is based on annual data from 1950 to 2005. So I've started off here with an ARDL11 model. It's included one lag on DY and one lag on stock building here. And when I estimate the equation here, I get a fairly well specified equation. There's no evidence here of any autocorrelation, heteroscedasticity and so on. I'm just going to have to take my word for that rather than go through the details of it. But if we look at the equation, we see that there are insignificant right-hand side variables. In particular, the two lags here, the lagged change in GDP and the lagged stock building, are both insignificant. So this equation could, in principle, be simplified. We could start to eliminate insignificant variables. Suppose we try eliminating both those insignificant variables. That would just give me a straightforward, if you like, basic or static regression equation between stock building and the change in GDP, as given by this equation here. I've imposed two restrictions on the original model in order to get to this equation. So what I'm going to do is do an F-test for those two restrictions. And the F-test is the standard F-test. It's based on the difference between the restricted and unrestricted residual sums of squares. And if we use the standard F formula, we get 6.965. The 5% critical value for an F-test of 2 restrictions and 52 degrees of freedom would be 3.16. So actually in this case we reject the null hypothesis. We've imposed those 2 restrictions, but if we do an F-test of them, then we can't accept that those 2 restrictions are valid. If I just go back one slide, you'll see that's despite the fact that both those variables that we've excluded have got quite low t ratios, 1.25 and 1.15 respectively. So individually they're both insignificant, but when we test the joint restriction that they both have parameter equal to 0, then we reject that restriction. Okay, so this points out one of the pitfalls of general to specific modelling. It's dangerous to impose too many restrictions all at once. The best strategy is to go through gradually and impose restrictions one at a time until we end up with the model that we settle for. So in this case, for example, we might eliminate the least significant variable, which is the lagged stock building variable, and we get then a finite distributed lag model. We get stock building is a function of current change in GDP and the lag change in GDP. And this is the equation we get there, just imposing the one restriction. We know that that restriction is valid because we can do a t-test for it. And this is a better specification than we obtain by imposing 2 restrictions at the same time. Okay. Another question we could ask actually here is the autoregressive error model an acceptable simplification of this? Okay, so suppose instead we'd estimated an AR1 error model. I've done that here using the particular software here that's using the Corcoran-Orcutt method, and I get the equation represented here where I've estimated 2 parameters, one on the current change in GDP and one is the autoregressive parameter. Now, we run into a problem here, because if we want to test this restriction, if we want to test whether or not the AR1 error model is an acceptable simplification of our original model, then we can't use an F-test, because the AR1 model involves a nonlinear restriction in the parameters. This is something we talked about in the previous lecture. So how can we test this? Well, there is a test which is based on the work of Sagan and was revived in 1978 in a paper by Hendry and Meisen in the Economic Journal. And they argue that you can test this nonlinear restriction using the following test. We take t, the sample size, multiplied by the log of the ratio of the restricted and unrestricted residual sums of squares, and under the null hypothesis that the restriction is valid, this follows a chi-squared distribution where, with q degrees of freedom, where q is the number of x variables on the right hand side of the equation. We should note that this is a large sample or asymptotic test, so we should only really interpret this when the sample size is getting reasonably large. I think here, with a sample size of 56, it is a reasonably large sample. Anyway, in this particular case, the test statistic is 56 multiplied by the log of that ratio of residual sums of squares. That gives a value of 20.47. The 5% critical value for q equals 1, because we've got one variable on the right hand side, is 3.84, and therefore we'd reject the null at the 5% level. Therefore, the autoregressive model isn't actually appropriate in this particular case. That's a little bit of an aside, but nevertheless I think it's an interesting aside for the purposes of this discussion of general to specific modelling. Okay, now suppose we've ended up with a model that we are now satisfied is a reasonable representation of the data. The problem with the general to specific approach is that we often end up with a model that's very hard to interpret from the point of view of economic theory. And a good practice is to try and write the model in a way that makes it easy to interpret. And one way we can do this is by use of what we call the error correction model. Suppose we have a general autoregressive distributed lag model. This is an ARDL11 model. It's got one lag of X and one lag of Y on the right hand side. Now, just by rewriting the model, by changing the way in which we set it out, we can write it in a way that looks fairly forbidding but actually can be interpreted in a more sensible way. This is the autoregressive distributed lag version. We can write it as delta y equals beta 0 plus beta 1 delta x plus beta 3 minus 1 multiplied by this expression here in parentheses, y t minus 1 plus beta 1 plus beta 2 beta 3 minus 1 xt minus 1 plus ut. This looks pretty forbidding until you realise that the expression in parentheses here constitutes the equilibrium relationship between y and x. Basically, we've separated this equation out into two parts. A part that depends upon deltas or changes in the variables, which represents the short-run relationship between y and x, and a part that represents the relationship between the levels of y and the level of x, which constitutes the long-run relationship. This is what we call the error correction form of the model. The neat thing about this representation is that all the parameters which we would obtain if we were to estimate this version can be given a sensible economic interpretation, which is not the case for the more general ARDL model, which is much harder to interpret. So basically, these are the important features of the error correction model. Firstly, it gives you a relationship between the growth rate or differences of the left-hand side variable and those of the right-hand side variables, which captures short-run adjustment. Secondly, it gives you a relationship in levels between the variables, which describes the long-run equilibrium relationship. And thirdly, it gives you an estimate of the parameter which describes the speed of adjustment when the variables are away from long-run equilibrium. It links the short-run and the long-run relationships. It's important to note that there is always an algebraic transformation which allows us to write the ARDL model in error correction form, but some of the variables some of the estimates of the parameters may indicate that some of the variables here may not be significant when we estimate it. Okay. Let's just look a little bit more detail at that issue of how we interpret the parameters. If we take our expression here, this is our error correction expression, then we can interpret each of these parameters as follows. First of all, the beta 1 parameter, that's the parameter on delta xt here, gives us an estimate of the short-run response of y to changes in x. So it's a straightforward short-run relationship. Secondly, if we take these term in parameters here, then this parameter here, beta 1 plus beta 2 over beta 3 minus 1, is an estimate of the equilibrium or steady state response. It's telling us that if x changes by some permanent, there's some permanent change in the x variable, so it's permanently higher, by how much will y change in equilibrium. Finally, the coefficient beta 3 minus 1 here measures the speed of adjustment. It tells us if there's a deviation from equilibrium, so if y and x are not aligned in their equilibrium relationship, how fast does y change in order to bring that relationship back towards equilibrium. So that's what I mean when I say that all these parameters have got sensible economic interpretations. We can divide them up into short-run response, long-run response, and the speed of adjustment here. Okay, let's look at an example. This is an ARDL11 model for UK imports. So I'm regressing here the log of imports on GDP, lagged GDP, and lagged imports. If we estimate it, then you see that all the coefficients are statistically significant. The T ratios here are all well above the critical value. So it indicates that we, straight away everything is significant. However, it's kind of hard to interpret the coefficients here And what do these coefficient estimates actually mean, or how do we interpret them in terms of economic theory? Well, before we get into that, one thing to note straight away is that we can calculate the equilibrium response very easily. We just add up the coefficients on log y and divide by 1 minus the coefficient on lagged imports, and we get a coefficient here of 2.16. So we say in the long run, a 1% increase in GDP produces a 2.16% increase in imports. Okay. Now let's turn to the error correction representation. Here, what I've done is regress the change in log imports on a constant, the change in log GDP, and then the lagged levels of imports and GDP. How do we interpret the coefficients now? Well, the coefficient on d log y is the short run response. If there is a 1% rise in GDP, then in the short run, import demand increases by 1.94. Okay. If we were to calculate the long run response, then we could do that quite straightforwardly. What we would do is we would take the coefficient on log y minus 1 here, and we'd take the coefficient, yeah, that's right, take the coefficient on log y minus 1, divide by 1 minus the coefficient on logged imports here, okay, and that would give us a value of 2.16. That's how we got our previous estimate. Okay. Now, it's important to note that this equation is just a different way of writing the ARDL model. We've not actually changed anything here. All we've done is take our existing equation and write it down in a different way. That means that we can estimate those parameters of interest using this formulation. So, for example, here, our coefficient on lagged imports here, 0.09, okay, is equal to the speed of adjustment. It's telling us how fast the imports will adjust if we're away from equilibrium, okay? And we see here that it's telling us that it's a value of minus 0.09, so it's telling us that we get about a 10% adjustment in every time period. Incidentally, I just realised I said before the calculation of the long run formula I gave you was incorrect. It's much simpler actually in this case. It's just the ratio 0.199 divided by 0.09. That's what gives you the 2.16. So my apologies, I misspoke earlier. One thing to note about this is that the R squared is much lower than it was in our previous regression equation, but you shouldn't interpret that as being a reduction in explanatory power. It's the same equation. All that's happened is we've changed the definition of the variable on the left hand side of the equation from the level of imports to the change in the level of imports, and as a result the R squared has changed because we're measuring a different thing. We're using a different benchmark here, and so this doesn't indicate any loss of explanatory power here. Okay. In fact, this is actually quite high explanatory power for an equation where we're trying to explain the difference in a variable, because we've taken out the trend from the data. Okay. You can actually see that this is the identical equation. If you compare the standard error, the regression, the Durbin-Watson statistic, then they're exactly the same in these two versions of the model. Okay. Why do we bother with this? Why use the error correction model? Well, basically, the parameters have got more natural economic interpretations than those of the ARD model. And secondly, it does actually provide a convenient way of testing for whether or not there is a long-run relationship between the variables. If we've got a non-zero speed of adjustment, then it indicates that we are moving towards the equilibrium. So the coefficient on the lagged endogenous variable needs to be significantly negative if there is an equilibrium relationship between the variables. In this case, the coefficient is minus 0.09. It's got a t ratio of minus 1.92. Now, we'd normally say that is pretty close to being significant using a standard t-test, but we've got to be a bit careful here, because the distribution of the estimator for that coefficient of the length endogenous variable is non-standard. It doesn't follow a t-distribution under the null, and in fact the appropriate critical values are somewhat higher than the t-critical values. So this is actually not nearly so significant as it appears in this particular equation. Okay, so that's one example. Let's finish by looking at another example. In this case we've got much longer lags, because in this case what I've done is look at quarterly data for consumption and income. So I'm basically estimating a consumption function. And I start off with a general model which includes lots of lags on all variables. In this case I've got 4 lags on income and 4 lags on consumption. And I fit my regression equation, and in this case you see that there are actually lots of coefficients which are insignificant. We've got lots of t ratios here which are much less than the t critical values. So I now want to progress to the stage of getting a parsimonious specification. So what I do is start to eliminate insignificant variables, but I'm fairly careful about how I do it. I don't just eliminate all insignificant variables at once. I start off by looking for the least significant variable, eliminate that, re-estimate, check again for what's now insignificant, and progressively eliminate insignificant variables. So here the least significant variable would be this one, Ly minus 1, because it's got a t ratio of 0.11. Okay? After I've gone through that process, I end up with a model in which all the variables I retain are statistically significant. So we'll look at the t ratios here, apart from the constant term which I've retained because lots of statistics use the constant term to construct test statistics. Everything else is statistically significant at the conventional level. In fact, what I've done is I've imposed 4 restrictions here. I've eliminated Ly minus 1, minus 2 and minus 3, and I've eliminated Lc minus 3. So I want to do a final test where I test all 4 restrictions simultaneously. So if I do an F test for that, I compare the residual sums of squares from the restricted and unrestricted models. When I impose those 4 restrictions jointly, I get an F statistic of 0.56. So I don't reject those restrictions either individually or jointly. So this is my parsimonious specification. Now what I want to do now is write that in